Hi and welcome back to Showsters classes. Today we'll be dealing with shapes and sizes of orbitals. Starting off with the s orbital. The orbitals are spherical and symmetrical about the nucleus. The probability of finding the electron is maximum near the nucleus. Let us first mark the nucleus. This central portion is called the nucleus. The first outer covering, that is the first outer covering, is the 1s orbital. Next, this white marked space is known as the radial node. Please keep this in mind because they usually ask this kind of questions for the MCQs. And lastly, the outside region is the 2s orbital. We'll also mark the axis. This is y, this is the z, and this, or somewhere over here, it will be x. The size of the orbital depends greatly upon the value of the quantum number n. Greater the value of n, the larger the size of the orbitals. That is, n rises, size also increases. Therefore, 2s orbital is larger than 1s orbital, but both of them are non-directional and spherical, symmetric in shape. Notice there is no radial space, that is radial node, for 1s orbital since it starts directly from the nucleus. Now for the p orbital, the probability of finding the p electron is maximum in two lobes on the opposite side of the nucleus. This gives rise to a dumbbell shape for the p orbital. For p orbital, L equals to 1. Let us write this down. L equals to 1, m equals to -1, 0 and +1. Thus p orbital have three different orientations. They are designated as px, py and pz. They are designated due to the electron having its maximum along the x, y and z axis respectively. As they are not spherically symmetric, they have directional character. The two lobes of the p orbitals are separate by a nodal plane, where the probability of finding the electron is 0. That is the line that is at this portion, the middle portion, the probability of finding an electron. The three p orbitals belonging to a particular energy shell have equal energies and are known as what we can term, or rather is usually termed as, degenerate orbitals. Now for d orbitals with L equals to 2, hence we can find the value as m equals to -2, -1, 0, +1 and +2. Thus there are 5 d orbitals. They have relatively complex geometry. Out of the 5 orbitals, the 3, that is dxy, dyz and dzx, project in between the axis, and the other 2, that is dz square and dz square into y square, lie along the axis. That is, this is how it looks like. This is the dyz, the dxz, the dz square, dxy and dx square y square, as we have already figured it out. Now for mathematical forms of orbitals, we find for n equals to 1, there is only one orbital, that is 1s equals psi 1, 0, 0. Now for n equals to 2, let that be number 2, which is for n equals to 2, that is energy is minus 328 kilojoule per mole. There are 4 atomic orbitals, that is phi 2, 0, 0. This is the 2s orbital. Phi 2, 1 plus 1. Next is the phi 2, 1, 0. These are the last one terms for the spins, that is 2, 1, and as expected it will be minus 1, and this whole constitute the 2p orbital. Moving on for n equals to 3, that is third for n equals to 3, there are 9 orbitals. We'll be listing them all. Phi 3, 0, 0, which is nothing but the 3s. I'm not writing the orbitals since it is gonna cost you some time. Phi 3, 1, 1, phi 3, 1, 0, phi 3, 1, minus 1. This is a very mechanical process and it's very easy to understand. Let us write this as 3p, and since this will have a 3d orbital, therefore phi 3, 2, minus 2, phi 3, 2, minus 1. Let's proceed serially. Phi 3, 2, 0, phi 3, 2, can you guess it? Yes, it's 1. And lastly, it's phi 3, 2, plus 2. And this constitutes the 3d orbital. And for several other, that is for n equals to 4, the total numbers, I'll just write it down. For n equals to 4, total numbers of orbitals will be 16, including 7 4f orbitals.